Our Technical Achievement Awards recognize individuals that have made significant contributions to the field. And these are really leaders in the field who have changed the path in computing.
So I'm getting this award for work done in development of multi-learner systems. A learner essentially builds models from data. So these are data-driven approaches to understanding things and systems and phenomena. So I got in this area kind of accidentally. A long time early in my career, I had a grant from DARPA on trying to classify sonar transient signals. These are underwater signals, and they're trying to, of course, find out who's producing them. These could be shrimps or ice or whales. Of course, DARPA might be more interested in submarines and things like that. And what I found is that there are very different ways of characterizing these signals. So you could use FFT, Gabor wavelets, and so on. And there are many different ways of building statistical models that use these characterizations and try to predict what's being observed.
Yeah, so I was recognized with this award for my work on microfluidic biochips. This is also called Lab on Chip, an emerging technology where the idea is to miniaturize the analytical instruments used for biochemistry and shrink it down to the size of a small chip so that we can have very small volumes that help us to speed up reactions. We can do things at much lower cost and to do these things much faster. So I have been focused on looking at some of the architectural and the optimization issues in this domain for the last 10 to 15 years.
The work I've been recognized for is about contributions to shared memory multiprocessor architectures and speculative multithreading. This means that what I've done is improvements and designs to make shared memory multiprocessors more programmable, faster, and more energy efficient. In particular, things that we have been doing in the past 15 years are understanding the concepts and issues behind speculative multithreading. And some of this work has had impact on transactional memory. I have also looked at and designed more efficient cache coherence protocols and novel shared memory architectures and organizations and programmable execution models for them. And I have also designed new techniques to make multi-cores more energy efficient, something that we call extreme scale computing.
This award recognizes my contributions to the software-based component composition and standardization. This key point for this work is to use software architecture in the whole software lifecycle to promote component reuse. Actually, this work comprises 3 parts. First, I develop a software architecture we call it SA-centric approach called the ABC. It's an architecture-based component composition. So this approach automates the development, deployment, maintenance, and evolution of component-based software systems.
So my thesis was, PhD thesis was actually in high-performance computing, and I developed a paper machine with 64,000 processors. Well and good, I didn't have to make it, so it didn't cost me anything. But I had to justify its existence, so I said, hey, let's simulate the human brain on this machine. So I started looking at brain mechanisms, and this was in 1986, and there was an emergence of interest in these so-called neural networks. So I attended the first neural network conference in San Diego in '87. I got very interested, very intrigued, and at some point I said, this is more interesting than processing. So instead of trying to simulate these networks on the human brain, I just tried to understand better what these networks do.
I started working in this topic around 2000. I had some colleagues at Duke who were exploring some of the low-level fabrication issues and the technology issues of manipulating droplets of liquid of very small volumes, nanoliters and even picoliter volumes. And I realized that we could think about these droplets as carrying biochemical payload. And these are bits of information which could manipulate it electrically. So we could think of building this up into a system with its own architecture. And there are a whole lot of interesting optimization problems that come into play. For example, how do we schedule the different fluidic operations? When does each operation get executed? What kind of mapping do we do? How do we execute these operations on specific functional units on this chip? And finally, what kind of droplet transportation pathways we're going to have? How are we going to transport the droplets from one part of the chip to another part of the chip?
So during my college years, I was intrigued and very curious about how computers work. And so I wanted to understand the innards of the computers. It turns out that the timing of my graduate school was perfect. So at that time when I was doing my graduate school, masters and PhDs, people were very interested in shared memory multiprocessors, scalable machines, and there were a lot of works and people coming up with new ideas and concepts. At that time, people thought that parallelism could be solved at that point. That means developing machines that were easy to program and that everybody will be programming parallel computers with high performance, right? High performance parallel computers.
So I entered this area in 1990s. At that time, Professor Fu Qingyang at Peking University. So they did a project called the JetBoard. So the JetBoard project is the largest software project getting continued 15 years support from the Chinese government. This objective of this project is to develop software engineering tools and environment to support the shift from the handicraft workshops to industrial production of software industry in China.
It's really a very unusual and exciting time enabled through the World Wide Web and other technologies. So the possibilities are endless. Much of what I did was self-learned, self-taught, because as I mentioned before, my thesis was in parallel computing and not in machine learning or data mining. So that keeps me forward, just keep on reinventing myself, because there are just so many. Once you understand the underlying mathematical principles, you can easily look at a new domain and come up with good answers.
Whenever you provide a solution for something and it doesn't work, right, don't get discouraged. And what we do is we try to understand what the problem is, why it doesn't work, and then try to provide a better solution.
I don't think of myself as being specialized in just one domain. I think specialization is a thing of the past. I think of myself as a very inquisitive researcher. I'm very curious. I'm always interested to learn about what other people are doing. I love to talk to people. I like to hear their experiences. Because this is how we improve ourselves.
And my motto is, if in Chinese, we could 志存高远，脚踏实地. In English, is aspire for high and ground, while planting our feet firmly in the ground. So everyone may have a dream. To make a dream come true, it is necessary to set some goal and makes you a long-term plan.
This is a wonderful organization. I think I'm very proud to be a member of IEEE CS.
In my research career, I benefit a lot from IEEE Computer Society.
I think that we are very fortunate to have an institution that helps our professional activities the way the IEEE Computer Society does.
I've been quite amazed by how nimble IEEE CS is.
It's important for the computing industry to come together and recognize people who've made a real impact. And our Technical Achievement Award winners are those people. So as I look across the technologies that they've implemented, that they've discovered, it's amazing to me how much what they've done has directly impacted not only computing, but because computing impacts and improves the human condition, each and every one of us has benefited from what they've done.
Well, they say it takes a village to raise a child. I think professors need a bit more help. So I'd like to thank my teachers. Actually, I have two in the audience. I didn't expect to see them, Victor Prasanna and Jean-Luc Godiot. So it was a very pleasant surprise. And I'd like to thank Professor Vipin Kumar for nominating me and my letter writers for their effort.
I told my younger son that I work on microfluidics. I'm actually making pipes on a chip for transporting fluids. And my son went to school and told his friends that my dad is a plumber. So that's... I'm very honored that IEEE Computer Society has chosen me for the award. This is not just an award for me, it is for my students, my collaborators.
It's my great honor to be here to receive this award. This award recognizes my work in the past years in the software area. I would like to thank the IEEE Computer Society to make it possible.
So these have helped me in my career over the years. I also would like to thank my students, past and present. It's been a joy to work with them, and it's really their expertise that has contributed in no small measure to what we're seeing here today.
Winning this award, of course, is a great honor. But at the same time, I feel that it's very humbling to see that I owe a lot to many people.
Thank you.
Thank you very much.
Thanks again.
Thank you to the IEEE Computer Society.